Good morning. Welcome, everyone. Welcome to the session titled Leading the Way in Climate and Energy Innovation, hosted by the University of Calgary this morning. My name is John Alho. I'm the Associate Vice President for Government Relations at the University. The University of Calgary is one of Canada's top research universities. We're ranked top 6 in the country and amongst the top 200 in the world. We have over 38,000 students, and this past year, we did $588 million worth of sponsored research. And speaking to the relevancy of that work, 35% of that funding comes directly from partnerships with industry, folks like you. We have intentionally built out a comprehensive innovation ecosystem designed to take ideas from lab straight to market, and have spun out almost 100 companies over the last several years, more than any other Canadian university or any other university in the country. As you'll see from my colleague's presentation this morning, this is only the tip of the iceberg. It's my pleasure here this morning to introduce to you our two speakers. Both are well-known and renowned scholars in energy and climate. And so first, and without any further ado, Dr. Ian Gates, who's the University of Calgary's Associate Vice President for Research and Innovation. In this role, he leads the innovation, technology transfer, and commercialization efforts across the university. He also serves as Director of the Global Research Initiative in Low Carbon Unconventional Resources and is a professor within the Department of Chemical and Petroleum Engineering. Dr. Jewel Bergerson is also speaking today, and she's also a professor in Chemical and Petroleum Engineering. She holds a Canada Research Chair in Energy Technology Assessment and leads an interdisciplinary research on energy technologies, focusing on life cycle assessments and community-driven solutions aimed at improving decision-making in the energy sector. She also will soon be leading, soon to be announced, so getting a bit of a sneak peek here, but we haven't rolled it out yet, but she will soon be leading the University of Calgary's new Energy Research Institute. So with that short introduction, Ian, Jewel, over to you.
Thank you, John. So what I'll do is I'm going to go through a set of slides and we'll talk about energy and emissions research at the University of Calgary. And, and then I'm going to hand it to Jewel and she'll go through a set of slides. So let's go to the next slide. Okay, so just a brief background on University of Calgary. So University of Calgary is in the city of Calgary in that beautiful Alberta. You know, it's a fairly young university, 50 something years old, 14 faculties, 5 campuses, and 38,000 students, of which about 6,000 students, 6,000 are grad students and postdocs. So in terms of research income, about $590 million now per year of research, and a whole lot of it being in energy. And, you know, we have an energy research strategy, which is really focused on the idea of energy solutions that are relevant, you know, so technologies and fundamentals so that we can empower how energy moves and the needs of today with respect to clean energy. So next slide. Oops. So, you know, there's a history of at U Calgary of energy across all the faculties. So a whole lot going on in engineering and science. But, you know, you look at humanities, law, business school, we have an immense set of programs that have been going on for decades with respect to energy. And some of these are listed in this slide here. So we have this really focus on transdisciplinary research with respect to energy, because energy solutions are not simply about technology, a machine. They're about social adoption, finance, and other issues. And that's what we focus on. We're looking at real solutions to energy challenges that we face. So next slide. So what I'll do is I'll do a very quick overview of academic programming. So when I talk about that, I mean talent and programs, internships, and so on. So let's go to the next slide. And, you know, of course, in engineering, we have bachelors of chemical, mechanical, energy engineering, geomatics, and also master's programs. And these programs, a huge amount of focus on energy related matters, environmental engineering matters, and so on. So in there, we have the petroleum engineering program, and that went through a lull because of demand, but now it's being brought back to life with it coming with admissions for 2025. So we're very proud that is now coming back. And that program's being expanded. There'll be aspects of it in geothermal, there'll be aspects of critical minerals and hydrogen and other things. So it's no longer just oil and gas. It has oil and gas, but it's certainly been expanded to these other energy areas. Let's go to the next slide. So the exciting thing from Faculty of Science is the Energy Science Bachelor's, which is launching in 2025. This is what used to be the Department of Geoscience, now the Department of Earth, Energy, and Environment. And this will be a program focused on energy science. So it's about really educating students about energy science with respect to basics for renewables all the way to fossil fuels and so on. Let's go to the next slide. So public policy, we have the Sustainable Energy Development Program, which is a transdisciplinary program offered with many different faculties involved, taught by different faculties. And we have students in there, which, they look at the intersection of technology, policy, and energy development, technology development, and so on. So, and economics, finance, and all of that. So a truly transdisciplinary program. And of course, the Master of Public Policy is also there. And the next slide. And the Faculty of Law, we have a joint law programs with University of Houston and University of Houston in international energy. And also we have the natural governances programs. Next slide. And then the School of Business, a huge amount of work on energy and commerce and so on, and also innovation. So there we have the GEMBAR program, the Global Energy Management Sustainable Development Programs, which are focused on energy and how we transition. So let's go to the next slide. And let's now talk about research. And in there, we have these programs which train students, which are incredibly valuable. They fill jobs in industry and government and other places. But of course, we have research, and these are the grad students and postdocs, and a huge amount of talent creation there. And they also go feed into industry, other universities, government, and so on. And in this, when you look at research, we think of it as not just about scholarship, so the thing of discovering something, but also the idea of commercializing that or getting out as a social innovation impact to society. So there's aspects of startup and technology development within the research realm. Let's go to the next slide. So we have many programs. So the one that the GRI that John mentioned earlier, $75 million program in energy, unconventional resources. And so there's a whole set of outcomes I'll talk about in a minute that has come out of that program. Quite a lot of research being funded by industry, also from the federal government and provincial government. Essentially we have an incredible ecosystem of energy research going on, funded by not only the government, but also our stakeholders with respect to end users. So it becomes quite a powerful research agenda within the university with respect to energy. So let's go to the next slide. And here's a partial listing of companies that we have worked with within the GRI. So that $75 million program, this is a partial list of companies that have worked with us, with our researchers, to advance solutions with both fundamental and applied contributions to help solve the challenges these companies face. Let's go to the next slide. And, within the placement of these things, when you start looking at energy related research themes, so what you see here is that within themes that we focus on historically within the University of Calgary, our ranking within the world. So you have the North American ranking, you can see that we're number 1 or number 2 in all of these categories. The categories being, petroleum, heavy oil production, asphaltenes, unconventional recovery, and so on, hydraulic fracturing. And what you see on a world stage, we are up to number 1, up to number 5. So we have done incredibly well as a university with respect to the research programs that we are running. Let's go to the next slide. And if you go further than that, and you start looking at impacts, scholarly impacts across the planet with respect to University of Calgary, in a set of topics in areas where we focus on in energy, and fonts are way too small for you to read, but I can list that there are a lot of petroleum in there. There's electrification and also decarbonization, CCS, and other things in there. So you put all those together and you aggregate those, and when you do those statistics, you go to the next slide. What you see is that we are number 1. So our global presence with respect to energy is remarkable. We are contributing on the world stage, and we're very proud of that. And, and this is against, massive schools like UT Austin, Stanford, and many other universities. So we're doing amazingly well as a powerhouse university with respect to energy research and outcomes. Let's go to the next slide. And, in Canada, if you start ranking us against the U15, so U15 is the 15 biggest universities in Canada with respect, research intensive universities in Canada. And there's the top 2% list, which lists the top 2% of researchers in an area, this one being energy, in the world. And at the University of Calgary in energy, 28 of our faculty members happen to be in the top 2% of energy researchers in the world. And if you were to look at the other major U15 universities, what you see is we are number one. So the next highest is University of Waterloo with 14, University of Alberta 14. So we're doing amazingly well. Our focused research agenda with respect to being both useful and fundamental at the same time has really borne out by our rankings with respect to energy research. Let's go to the next slide. And so the type of research we're doing now, we're very focused on, finding solutions to the challenges we face, in particular for Alberta and Western Canada, but also globally. So we're doing quite a lot of work on unconventional resources. How do we do better carbon management with respect to unconventional resources? So, for example, instead of using steam, using solvent for recovery of oil, and also natural gas injection or CO2 injection to help that. So a huge amount of work going on in unconventional resources, in enhanced oil recovery, also drilling wells, completion design, well planning, how do you optimize a reservoir production strategy using better wells, and also a whole lot of work in methane, natural gas with respect to processing, conversion, emissions reduction, hydrates, and so on. Hydrogen, a massive amount of work on storage, transportation, generation from several methods: electrolysis, pyrolysis, gasification, and so on. Geothermal, we have a chair in geothermal energy, CCUS. So those are very active a focus with respect to not only simulation work, but also practical work with the CAMI facility south of Calgary. And that does, CO2 monitoring, containment, sequestration. We're also looking at EGR, so enhanced gas recovery, combined geothermal and CCS, and of course, carbon conversion. A lot of work in electrochemistry, so energy storage. That's all going on with respect to batteries, fuel cells, capacitors, and other things. Wind energy, solar, data analytics, and machine learning applied to energy systems to optimize these so we can do better control of such systems and also glean intelligence of these systems. Environmental energy policy development, water and energy systems analysis, sustainability life cycle assessment, and so on, which Jewel will talk about later as part of her research. So a huge amount of energy related work, emission related work that is really quite hard hitting with respect to our industries that we have within Alberta and in Canada and globally. So we're about finding scholarly impacts, the fundamentals, but also those empower application to solve the challenges that we face. So let's go to the next slide. So here's some examples of outcomes that have come from our research with respect to commercial outcomes. So what you see here is you see companies that have evolved out of our research. And so CMG, reservoir simulation company, HiCal, massive lab company, HISIS, a process simulation software used globally. So a huge amount of outcomes that have happened at the University of Calgary where we built and conducted fundamental research that empowered application and solutions for people to use. So a huge amount of that going on. And yes, we are the #1 startup creator with respect to companies over the last 5 years, and certainly in energy, many of them are in the space of energy. Let's go to the next slide. We also have partnered with others with respect to innovation. So we have, through our technology transfer office, the Energy Transition Center, which is an innovation hub, and it's really about that embracing of industry. So how do we better interact with industry and young startups and the community of innovative energy folks? So we have this hub there to create a space for conducting that type of interaction. So let's go to the next slide. So now I'm going to give some specific examples of outcomes with respect to energy and carbon management. So let's go to the next slide, and we'll go through this pretty quick. But in terms of CO2 capture, you start to break down all of these subject areas, direct air capture, industrial process streams, direct ocean capture, and you start looking at the various options that we currently have within let's say direct air capture, dissolution, adsorption, membrane separation, mineralization, electrochemical processes, and so on. And what you find is that you can break down all of these into very specific research challenges that we face. And those challenges are usually associated with material science, the cost of the operation, and so on. And so you have all of these things happening, and you have materials that you have to research to enable these types of processes so that they're both effective and they're economic, right? And if you were to then look at this and you click the next, you see the researchers that we have at the university tackling these types of problems, so CO2 capture. So we have a huge amount of folks in chemical engineering, chemistry, all the way to policy folks working on these types of capture activities. And you start looking at the example impacts from that. Carbon engineering from U Calgary, David Keith sold to Occidental, CAF 20. It's a metallic organic framework licensed to Savante, that's from George Shimizu, and Synergia from Mark Strauss. It's a biocapture plant for basically building algae. So you absorb CO2 in algae, and from that you can then get a dye, a food dye that's all natural and safe, right? But you also now are taking in the CO2 and convert it into another material. Let's go to the next slide. So there, we've done a lot of work, with respect to these types of materials, and you can start comparing them. BFAC4, that's a bitumen-based one. I'm very proud to say that bitumen is a very versatile material, and with its basic groups on it, loves to grab gas. So it's an amazing material to me. And so BFAC4, we're developing that as a material for CO2 capture, right? Instead of metallic organic frameworks, zeolites, and other materials. Super cheap to make. So something that is worth pursuing. So let's go to the next one. CO2 conversion, what are we doing there? So this is about the idea of take CO2 and convert it into more valuable products. And so you can then do chemical-based change. So that could be to fuels and other things like that. You can mineralize it into something useful, maybe for cement and those types of things. You can do biological conversion, that's into, let's say, biomass or other things, and then electrochemical conversion into materials, for instance, methanol and other materials using electrolytic methods. And out of that, you get a whole set of products. And who at the university is working on these topics? Let's go to the next click. And so we have a whole set of researchers in the activity section of CO2 conversion, and you have outcomes like electrochemical CO2 to alcohols. That's Kibria's group at the university with molten alloy technology. So this is one I'm actually doing, which is converting methane into hydrogen and carbon products, and 249 Limited, which is doing Fischer-Tropsch, Synergia, CO2 to dyes, and so on. So this is the chemical conversion of CO2 where it's both economic and it makes sense to do it. It bolts very well onto an existing infrastructure. Let's go to the next slide. And here's an example of SAF. So this is where we're converting using Fischer-Tropsch with a catalyst we've designed and a reactor system that's super thermally efficient so that we can convert things into synthetic aviation fuel on a daily basis. Let's go to the next slide. So now you have CO2 storage with use. So the idea is that you're going to put it into the underground, but you're not just about going to store it. You're going to do something with it to enhance another value creation activity. And so you have enhanced petroleum recovery, so EOR, EGR, so enhanced gas recovery, and so on. You have geothermal and brine, so you could use CO2 as the working fluid for a geothermal operation and lose as much of the CO2 into the formation as you can. And in doing so, it becomes a CO2 sequestration plus geothermal type process. And of course, food. We don't do much food. So that's one of our weaknesses at the university. We don't do much food research, but the other two we do quite a lot of. And so in that, we produce all kinds of technologies with respect to, for instance, geothermal or EGR and others. Let's go to the next slide. So a whole host of folks working in this, especially from geosciences. And then let's go to the next slide. And in there, there's examples of processes. This is designed for a offshore gas reservoir where we're using CO2 as a flooding gas to get more methane out. But the neat thing about it is the process is designed such that the amount of CO2 stored is equal to the amount of CO2 produced from combusting all of the natural gas that was ever produced in that reservoir. And in doing so, you're starting to design carbon negative natural gas, right? That is what you're building in this. So you have EGR type processes, combined geothermal CO2 sequestration. So the idea of instead of Shell Quest doing what they do with respect to injecting CO2 into the basal Cambrian. It's really about now how do we use that to produce energy out too, because it is sort of warm. Let's go to the next slide. And this is pure CO2 storage. And so you have onshore underground, you have offshore, you have surface based. And so if you look there with lots of targets for that out there, and click again, and there's a whole host of people at the university working in these areas with respect to CO2 storage with impacts like the Carbon Management Canada facility, and of course, partnerships we have with people working on CO2 hubs. So a whole bunch of things happening in this space as well. Let's go to the next slide. And so, yes, analyzing the Shell Quest project to look at, well, how do we do better? How do we make it more effective and more efficient? It's amazing what's happening there, right? So net 800,000 tons per year going in, 1 million injected, but it generates 200,000 doing it. So net, it's injecting 800,000 in. But there are aspects about it that we can learn and do better, right? So an amazing project, but a lot of research that can be done with that data set. Let's go to the next slide. And hydrogen. So we have a whole host of folks working in hydrogen with respect to generation, storage, transport, and end use. How do we use it as energy vector or feedstock material for chemicals? So a whole host of stuff happening with the impacts there. So Proton H2, C Victus, Chris Clarkson, I think they're presenting sometime here. And of course, molten alloy and this Mayank and Milana and a lot of other researchers at the university supporting hydrogen research. Let's go to the next slide. And here's an example of Proton H2. So this one is where instead of looking at heavy oil resources as oil, now think of them with the water in there as hydrogen. So you're looking at, instead of hydrocarbon and water, you're looking at hydrogen from both the oil and the water. And in doing so, if you gasify those reservoirs, you can produce hydrogen to surface, as we're doing right now. And the thing is that becomes a less than $1 per kilogram hydrogen source, right? So that is going on right now in Kindersley at our site. So less than $1 kilogram hydrogen, and that's just now about scaling up that technology. So you start revisioning heavy oil resources now as hydrogen resources, right? So let's go to the next slide. And this is molten alloy technology, where you start looking at these kinds of reactors where they just not only process methane, but they also process CO2 and degrade CO2. But the interesting about these is you start to now imagine the world of carbonless flaring, where you can flare, but you don't produce CO2 to atmosphere or methane. As methane slip, what you produce is carbon solid and hydrogen instead from a gas stream that might contain not so much methane in it, but very efficient at doing these types of things. Okay, let's go to the next one. So other carbon management activities. So you see electrochemical activities within lots of labs, nuclear emissions reduction. So that's the Natural Gas Innovation Fund. We'll be talking about that on Saturday. And Pomelo, which is Chris Hugenholtz's operation. And also a lot of work with respect to analyzing energy systems for decarbonizing them. And of course, geothermal activity. So let's go to the next slide. In terms of policy research, we have the School of Public Policy, and there we're looking at environmental, energy policy, emissions, climate, fiscal, economic policy, international policy, and trade. And there's a whole host of folks from multiple faculties working on these types of things. And there's quite a bit going on with respect to agricultural emissions. And I'll talk a little bit about that in a second. So let's go to the next slide. And so, I'm back one. And so this is, back or forward again and again and again. So this is Nziri. So this is Blake Schaefer, Simon Hastings Simon's work on electrification and electricity and the basis for it, and looking at it from a transformational change with respect to how do we move electricity to more less carbon intensive formats. So I invite you to talk to them about this, because I admit I'm not fully familiar with it. But let's go to the next slide. Here's another example of transdisciplinary methane research with Chris Hugenholtz, where he's looking at cities, and he's looking at, there's the city of Calgary, looking at methane, at airshed and other sensor data to look at how methane is evolving within a city. And of course, landfills are a major source of methane. So there's a lot to be done there with respect to avoiding those emissions. Let's go to the next slide. And so this Simpson Center, so this is from the School of Public Policy, where you're looking at how is methane being managed with respect to agriculture. And of course, cattle. Cattle is a major part of that. And so there's a lot of work there to look at how do we deal with carbon within the agricultural sector. So let's go to the next slide. And now we'll go to Jewel. So
Great, thanks. I'm still digesting all of that. That was a lot of information. Great. So my name is Jewel Bergerson, and I'm a professor in chemical and petroleum engineering. I do systems analysis. So my Canada Research Chair is in energy technology assessment. So I very much take a big picture approach to our energy system and look at the connections between different systems to look for opportunities as well as identify where there might be some unintended consequences as we develop technologies and deploy them. We want to make sure that we're getting the biggest bang for our buck and delivering the goals of the innovation that we set out. Looks like we're starting in the middle of the presentation, so we might just take a second to get back there. Maybe I can just talk about this. So this is one of our tools that we have, which is called Prelim. So it's a open that allow us to estimate the energy and greenhouse gas emissions associated with processing different types of crude oil through different types of refinery configurations. So we can reorient the process units to represent typical refining capacities as well as individual refineries. Okay. Yeah, so I'm going to talk about my research specifically to give you an example of the types of things that we're working on at the University of Calgary. And the idea here is that systems tools, I would put forward things like life cycle assessment, can be used to build transparent and credible systems to both set baselines as well as track emission reduction progress. And the unique aspect of the work that we do is that we actually connect these emission estimates across their supply chain. So rather than looking at the UNFCCC reporting or through the tier program or others, those are sort of sector specific. This allows you to actually trace things through the entire life cycle or supply chain to actually understand how the extraction emissions are connected into refining and so on. And that can be helpful in terms of actually demonstrating that emission reductions are occurring and that we're seeing those in real time as we track those over time. The other part of this is that we use this to actually help drive innovation itself. So through the systems analysis that we can conduct, we can actually identify where there are opportunities to improve the system. And we can sort of weigh the trade-offs of where do you get the biggest bang for your buck? Is it a particular set of technologies at the refining side? How does that affect both upstream and downstream, for example? And so we do work with folks on campus and elsewhere that are developing new technologies. We can also go in at an early stage and assess the sort of system-wide impacts, and that can help to give information about the priorities for research and development. So an example that I'll give is Viola Burse in chemistry, who is a fuel cell, international fuel cell expert. As she's going to design her next fuel cells configuration, we can give her input on the material selection that she's using. So she actually does the assessment of how do you actually assemble the fuel cell and the performance of that fuel cell. What we can tell her is if you've got 3 different materials that you're deciding between and they have relatively similar performance, which of those have resource scarcity issues or environmental impacts upstream and downstream that might affect the performance of the fuel cell over its life cycle as you move forward. And so we do collaborative work with researchers that are at the very early stages of technology development. And then I'll also highlight a couple examples of innovation that is occurring at the University of Calgary related to this kind of work. Next slide. So as I said, this is our prelim model, the refinery model, and you can click through the side here to get some of the details. It is at a process unit level, and it allows you to look at the flows of material and energy consumption at each process unit level. And if you go through, we've got different configurations, and we can actually look at the product yields and product slates. And so we can do this for existing refineries. We have represented 11 configurations, and so we can look at the typical refinery complexes. More and more, we're being asked to actually use this to represent individual individual refineries. And so a lot of the work in this modeling has been validating our estimates against industry data. So this has been with heavy collaboration with industry globally, looking at refining capacity and the estimates that are there. We've also worked with Alberta Innovates and ERA to work with oil sands companies specifically to look at how these estimates compare to some of the internal estimates and things like that. The good news is it's very close, 1 to 5% or so if you draw the boundaries in the same way. So the next slide. So we can then use that to look at the global perspective. So we can look at, in collaboration with industry, we get really rich commercial data sets that allow us to estimate the refining emissions associated with different refineries around the world. So there's refining greenhouse gas intensity. So this is kilograms of CO2 equivalent per barrel of crude that's processed in that country. And you can see the numbers on each of the countries is the number of refineries that we've represented. So we have 479 in total. And then we can actually estimate the crude flows into those refineries and the refining emissions. This was actually the first time that this has been done at a global scale, looking at this level of detail where you can actually look at the individual refining capacity and the intensities of processing these crudes globally. If we go to the next slide. This also required that we did some mapping. So the connections between these systems are actually generally quite weak in terms of public data to actually connect a field that's producing oil or gas. How that actually connects is transported and connects to individual refining capacity. And so on the left-hand side are the source countries where the crudes are coming from if they were processed in refineries that they're sitting at today. On the right-hand side is the destination country. So where the crude is actually processed. You can see the different types of refining configurations. So the different middle sections are the light, medium, and deep conversion refineries. And this just helps us make that connection. We had another paper that just focused on the crude oil trading and market policy implications. As I said, this is just the refining capacity, but to look at this from a full life cycle, we actually collaborate with folks at Stanford that have the oil and gas extraction model OPG. We also collaborated with MIT to work on the crude logistics. So actually mapping extraction through to refining to do that. So once we have that, then we have this sort of even playing field to look at the options for where do you go from here in terms of the refining and the emissions associated with that. We go to the next slide. This was an attempt at looking at just at a high level the types of carbon mitigation actions that you could take in refining capacity. So here we're looking at the cumulative crude refined globally. Each of the slivers that's there is an individual refinery around the world. The positive numbers there are the individual refinery emissions associated with each of those refineries around the world. And then the black lines are different investment decisions. So the lower dotted line is the high investment emission reduction scenario, and then the solid black is the lower emission. So the lower emission reduction scenario is things that might be economic to do today. So improving efficiency, if you don't have cogen, putting cogen in, and all the sort of low hanging fruit. The dotted black line is more aggressive. You would need additional climate policy and other things to actually enact that. But then what we can do is say what the net emission reduction would be. So the green is the emission reduction at the lower investment, and then the purple is the sort of really deep aggressive investment cases. So we can start using that then to get ideas of where could you get the biggest bang for your buck and what would be needed in terms of the incentive to actually make that investment, right? You're not going to go to that really stringent investment case unless there is a good policy and business case to make for that. But we can actually look at that and how that's different in different refining capacities around the world. So next slide. The other thing that we're doing, though, is actually looking at the refinery of the future. So this is the configurations we have, but I sort of see the refining as the sort of linchpin in the supply chain. So these are massive investments that are sitting strategically close to demand centers for products. What we know is that the demand for those products is shifting over time, and depending how aggressively we go after climate goals, you might have effects of a high penetration of electric vehicles in a particular market. That might drop the demand for gasoline in that market, but it's not clear that you're going to actually drop the demand for other products from the refinery at the same level. And so what we see is that a lot of the net zero scenarios that people are planning, that we have this sort of gradual decline in all products at a linear pace. And we know that that's not true for refineries. The other side of it is that there are massive opportunities for us to look at these refineries of how do we adjust those to be competitive in a range of future scenarios, knowing that the uncertainty of how aggressively we're going after climate targets is going to be different in different jurisdictions, and those opportunities of how can we supply a new product mix using this chemical conversion complex that is capable of doing lots of other things like CO2 conversion or gasification of the heavy ends that you could make use of for other types of products. Being a net hydrogen supplier is another idea of where you could go with this. And so we're trying to sort of upend this sort of static configuration that we've got right now to think more creatively about the ways that we might be able to do that. So there's a few animations here, if you could just maybe step through them a little bit. This is the new capacity that we're adding to our model to be able to look at some of those future scenarios to see what potential it has to, under what conditions might you want to invest in a gasification facility, for example. We have different products going into the refineries as well. So shifting crude oil slates, but also this interest in co-processing biomass options or plastics as part of a recycling scheme and things like that. So how do we take those into account? The next one. See if it comes up here. Yeah. So carbon capture is an obvious thing that we could think about in this place, but how might we do that in ways to actually maximize the benefit of that? So we have things like the reverse water gas shift reaction and Fischer-Tropsch to produce valuable products, right? There's lots of different ideas of ways that we could think about making use of the CO2 within this chemical conversion complex. The resids gasification that we might capture from, and then that offers possibilities for other conversion steps as well. Next one. As well as the petrochemical processes, right? And so we see some of this trend globally of if your gasoline demand is expected to drop, you might shift some of that fraction towards petrochemical development. What does that look like, and how might you do that in new and innovative ways? So this is just a quick example of the type of refinery of the future sort of analysis that we'll be doing. So what is the potential role of carbon capture in the US refineries in an uncertain future? So we have very good estimates of the cost dollars per ton of deploying carbon capture on different streams within the refinery. We can do that at a slightly more detailed level than has been done before. But really what we want to think about is under these uncertain future conditions, when would you actually deploy CCS? When would that actually make sense? And so thinking about that the crude characteristics are changing coming into the refinery, changing the demand for products, so shifting in demand for gasoline and diesel, but maybe having an increase in demand for jet fuel, for example. The magnitude of the climate pressure, right? That's a huge uncertainty in terms of how aggressively will we go after our climate targets, and how do we pace the level of investment that we might have based on different projections of that aggressiveness. Next slide. And so this is an example. We use what's called real options analysis, which is an economics tool, and it allows you to actually look at things in terms of probabilities. So we look at different trajectories of climate policy and the aggressiveness with which we might price carbon at a higher level. And here we're thinking about a societal cost of carbon, right? So not necessarily any particular policy, but just thinking about if we value reducing carbon at a certain level, and if that level is uncertain, we can apply different probabilities and play through the scenarios. And so this is looking at different futures. So this is over time. We're looking at different types of refinery configurations. So the light processing, medium, and deep conversion. And then we have different future scenarios for how much fuel demand there will be, right? And we see in even every net zero scenario that we've seen, you have some residual demand for gasoline, diesel, and other products coming out of the refinery. But how much demand you'll have in 2050 is not clear, and it'll be different in different jurisdictions. So we look at different demand scenarios. And then we offer the ability to either continue operating unabated within the refinery, deploy carbon capture, or eventually just shut down if the carbon price gets to a point where it is just not profitable to continue operating the refinery. And so this is one set that we can run. We can run through this for different sets. The different colors show you the different actions that they could take, and it's the most probable decision that you would make under those conditions. So what we see is that you're most likely to deploy carbon capture in the medium conversion refineries, and that's the most likely type of refinery that would survive under a future where you have aggressive climate policy. And this is a US case that we ran through. That is just one set of probabilities that you could have. If that's not the future that you want to see, then we have to think through what sort of incentives and technology options could we deploy to actually maintain the competitiveness of a different configuration and a different setup that we might have. Next slide. And so I was at a Alberta Innovates workshop a few weeks ago talking about the value added of the bitumen products, and particularly the heavy fraction of the barrel, and where do we see opportunities for that. From the life cycle perspective, we can simplify this quite a bit, that the inputs into your refinery and upstream as well need to be low carbon options for hydrogen and for energy inputs to reduce the carbon footprint of this step. If you take that bottom of the barrel and you try to do something different with it to derive additional value, the big determinant is going to be whether or not the end product is combusted or not, right? If it is combusted, then you need to think about the greenhouse gas emissions associated with that. If you can create a product that is not actually combusted, you have the opportunity of delivering more value for that bottom part of the barrel, as well as delivering a low carbon option. And so that's, lots of work going on at Alberta Innovates to actually focus on that and looking for innovative products. And so the last part, I'll just highlight a few of my colleagues that are actually working in that space, being supported by Alberta Innovates to actually look at that. So the next slide. So this is Viola Burse in chemistry, as I mentioned, and she's a world leading expert in fuel cell technology. And she's actually building the fuel cell itself and looking at different types of materials that you could use to actually create that the fuel cell. And so this is a key component of the hydrogen fuel cell is the MEA. And she's actually now using Alberta asphalt derived crude for this. And what she's seeing when she actually goes to test this material is that you actually see very good performance compared to the commercial comparison, which is the blue bar there, under different voltages that she's tested out in the lab setting. And then if you actually design the structure of the carbon scaffold using this Alberta product, you can actually improve that performance even further. So that's exciting from this perspective. I think it is relatively early stage, but it is really an exciting finding that she has as part of her research. And so there's been a spin-off company with her and some of her former students, Momentum Materials, that's moving forward. The next slide. This is my colleague, Milana Trifkovic, and so she's working, her research program really is all about taking what's considered to be low value or waste products and turning them into something more valuable. And so this is one of many things that she's working on, but this is particularly exciting as well. So she's actually using asphalt derived material to actually create these carbon dots, or ASPHA dots, she calls them. And it's actually a really versatile program. So it's just reorienting the molecules in different ways. But what she's seeing is that there's a very wide range of potential applications. And so looking at low temperature conversion of asphaltenes into biocompatible asphalt dots is one. Using it for friction and wear reduction, even into some of the medical applications. So tumor MRI imaging agents, cancer phototherapy, thermal therapy, a whole range of different types of things that she's looking at to apply this to. So really exciting in terms of the material science and the potential for applications, making use of the unique aspect of the asphaltenes that come from our bitumen. I'm going to not be able to say any more on this. So if you are interested, I can put you in touch with Milana if you want to hear more. Just one last example. And so this is our collaborator and colleague, Kibria, in chemical and petroleum engineering, who also has a startup company called Carbomat. And again, he's using these asphaltenes to derive carbon fiber, which has a whole range of possible implications as well. And so this is a few years into actually developing out this technology and bringing it to a whole range of potential markets that are associated with that as well. And so we can see that this value that could be derived from this part of the barrel is really promising. Excited that we can also do systems research to help give information about that broader perspective. Maybe with that, we can finish things up. Yeah. And oh, sorry, I did have one last colleague I wanted to highlight here. So this is sort of changing gears from the bitumen portion and actually looking at the CDR technology. So Ian had mentioned a little bit about this before, but these negative emission technologies that we're still wrapping our heads around, how do we define it at net zero? How do we think about the technologies that could play a role, and when and if we might want to deploy these types of technologies? So with this, we're looking at direct air capture with carbon capture and storage. So beyond reducing emissions from something we're doing today, this actually has a net effect on the planet that you're actually reducing emissions, reducing the concentration of CO2 in the atmosphere. And that's sort of the basic definition of net negative technologies. And so this project was actually funded through the ECCC, primarily, now has some industry funding as well. And it's a cross-campus activity. And I describe this as one of the most transdisciplinary projects we have on our campus right now. So we have not just our scientists and our engineers, but we also have political scientists, other folks in social science and humanities, to look at all dimensions of these possible technologies. And so looking at identifying and assessing the cost, environmental impact, and scalability of the CDR technologies. And I should say as well that there's a whole set of different carbon dioxide removal technologies. We don't focus as much on the nature-based solutions. We focus more on the direct air capture with CCS, as well as the bikers, it's called. So it's biomass with CCS for the purposes of negative emission technologies, as well as mineralization. And this is a collaboration of researchers across Canada, and bringing together that to assess the costs and environmental impacts, ways in which CDR deployment will be shaped by and shape law and governance, stakeholder and community perception. So there's a lot of work to go out and understand how people feel about this, what they might be excited about, what they might have concerns about, and how that should be reflected in regulation, as well as the actual design and development of the technologies themselves. Also, there's trade-offs that are inherent in developing supportive legislation and policies for CDR and the role that they should play in Canada's future. So with that, I will end there. Thank you very much for your attention, and happy to take any questions or comments that you might have. Thanks very much.
Thank you. Any questions?
That was a lot of material to go through. I feel like people may be processing it, but we have 10 minutes if there's any conversation or questions.
Or if you want the slides, just ask. I'll certainly send them and you can look at them later, digest them.
Great. Well, hopefully we can continue the conversation later today.